Fossil fuels. The world ran on dead planets for 200 years. When you press the gas pedal, you are releasing a 300 million year old beam of sunlight. Every time a car drives down the street, it's burning something that used to be alive. Not last year, not 1,000 years ago, about 300 million years ago. Here's the deeper truth. Fossil fuels aren't really dead plants. They're ancient sunlight. Those plants, millions of years ago, absorbed energy from the sun through photosynthesis. The same process happening in every leaf outside your window right now. That solar energy that got locked inside the plant's tissues. That plant died, got buried, got crushed, and the sunlight stayed trapped inside for 300 million years, until we dug it up and lit a match. When you press the gas pedal, you are releasing a 300 million year old beam of sunlight. We call the fuel fossil fuels, because they are quite literally the fossils of ancient life and ancient energy. How did plants turn into coal? The answer involves a giant pressure cooker. You might be wondering, why didn't the plants just rot? Normally, when a tree dies, bacteria and fungi decompose it within a few years. The carbon goes back into the air. That is the normal carbon cycle, and it's perfectly healthy. But something different happened 300 million years ago. Ancient forests were dying in vast swamps. When the trees fell into water, there was no oxygen at the bottom, and without oxygen, bacteria couldn't decompose them. The wood just piled up, layer after layer, at the bottom of ancient swamps. Then came the pressure. Over millions of years, the more sediment, sand, rock, mud, piled on top, thousands of meters of it. The weight was so enormous that it acted like a giant pressure cooker, squeezing out the water, the gases, the impurities, and concentrating what was left into pure, dense carbon. That is coal. Why coal and oil are made from different recipes. Oil and natural gas formed the same way, but from a completely different starting ingredient. And the difference in ingredients is why we ended up with two completely different fuels. Land plants are built from lignin, the tough, rigid fiber that holds wood together and lets trees stand upright. Lignin is mostly carbon and hydrogen locked in a hard, solid structure. When you compress it over millions of years, it stays solid. That is coal. But the tiny marine organisms that become oil, algae, plankton, microscopic sea creatures, are built very differently. Instead of wood fiber, their bodies are packed with lipids, fats, and oils. Think of the difference between a wooden plank and a bottle of cooking oil. When you heat and compress fat under enormous pressure over millions of years, it doesn't turn into rock. It melts, migrates through the surrounding stone, and pools into pockets of liquid. That is crude oil, and because lipids pack more energy per molecule than lignin does, oil releases more energy per liter when it burns. That's why jet fuel, which is refined from oil, can power an aircraft across the Pacific Ocean, while coal can't. Why did fossil fuels power the whole world? When humans started burning coal in the 1700s, it was a revolution. Suddenly, you didn't need horses or human muscles to power a factory. You just needed to dig up rocks and burn them. The reason fossil fuels became so dominant comes down to three things. 1. Energy density. Fossil fuels pack an enormous amount of energy into a small space. Because they spent 300 million years being compressed and concentrated. 1 liter of gasoline contains about as much energy as it would take a professional cyclist to pedal for 12 hours straight. No battery in the world today can match that. Number 2, portability. You can put gasoline in a tank and drive anywhere. You can ship coal across the ocean on a boat. Fossil fuels are easy to store and move, which is exactly what a growing civilization needs. Number 3, infrastructure. Over 200 years, humans built an entire civilization around fossil fuels. Pipelines, refineries, petrol stations, power plants, heating systems into every building. To understand how deep this really goes, try this thought-out experiment. Imagine that tomorrow, every gas station in the world closes. Sound good? Here's the problem. The trucks that deliver your food run on diesel. The cargo ships that cross the ocean run on fuel oil. The cement mixers building your school run on diesel. Most of them can't simply be plugged in overnight. Energy transition isn't like switching apps on a phone. It's more like rebuilding the entire city plumbing while people are still living in it and need water every single day. The problem? The blanket around the earth is getting thicker. Here's the core issue. When those ancient plants were alive, they pulled carbon dioxide out of the atmosphere and stored it in our bodies, using sunlight to do so. When they became fossil fuels, that carbon stayed locked underground for 300 million years. It was out of the atmosphere, out of play. When we burn fossil fuels, we run that process in reverse. We release carbon that has been buried for 300 million years back into the atmosphere in form of CO2 in a matter of decades. Why does that matter? Here's how it actually works, and it's more than precise than just quote-unquote a blanket. Sunlight arrives at Earth as short waves, high-energy visible light, and ultraviolet radiation. The atmosphere lets most of this through, and it warms the land, ocean, the ground. So far, so good. But the warmed Earth then radiates that heat back upward as long waves, a lower energy form of radiation called infrared. And here is the key. CO2 molecules in the atmosphere are perfectly shaped to absorb infrared long waves. They capture the heat trying to escape upward and send it bouncing back down to the surface. This is why scientists call CO2 a greenhouse gas. The atmosphere acts like a one-way valve. Short-wave sunlight passes through going in, but long-wave heat trying to escape going out gets caught and reflected back. In a greenhouse, the glass does this. In Earth's atmosphere, CO2 doesn't. Without any CO2, the heat would escape freely into space, and Earth's surface would average around minus 18 degrees Celsius, or around minus 0.4 Fahrenheit. A frozen, lifeless planet. The greenhouse effect in the right amount is what makes Earth habitable. The problem is we are increasing the amount of CO2 doing the catching. Since 1850, CO2 in the atmosphere has risen from 280 parts per million to around 420. Parts per million means for every million air molecules. 280 were CO2. Now it's 420. That 50% increase might sound small, but imagine adding 50% more salt to every glass of water in the world. You would taste the difference immediately. Earth's climate is equally sensitive. That extra CO2 means more infrared gets caught, more heat bounces back, and the planet's energy balance shifts. The planet's average temperature has already risen by 1.2 degrees Celsius. That might sound tiny, but Earth's climate is a system so finely balanced that 1.2 degrees is enough to melt glaciers, shift monsoons, and push species towards extinction. So why are we still using them? Here's the honest answer. Because fossil fuels are still incredibly useful, incredibly energy dense, and so deeply woven into the infrastructure of modern life that replacing them takes decades, not years. In 2024, the world got 80% of its total energy from fossil fuels, roughly the same share as 30 years ago. Renewables are growing fast, but total energy demand is also growing fast. We need more solar and wind every year, and also using more energy every year. Next episode, we are going to ask a harder question. The alternatives: solar, wind, nuclear. Are they actually as clean as people say? Here's something to think about. Burning wood in a fireplace also releases CO2. So why do scientists say it's less harmful to the climate than burning coal? Leave your answer in the comments.